So we can heckle DC quite easily. Yeah.
How long do I have to prepare? I emailed it. Yeah, I was like, can you come in? It is 12. It is 12:15. Are you hearing me? Is this on? Is this on? Is this on? Is this on? It is on. Good. Let's start. This is the first ever JILA Colloquium given by anyone from the staff, in particular the JILA Shops. So this is going to be an amazing experiment. I really hope that we're going to be able to repeat this at some time in the future. I'm going to introduce Thatcher, who's going to tell you what the format is.
Andrew, I would just like to add that if this goes well, the next JILA staff will put details of
Awesome.
yeah,
So before I get started, I don't know where James Fung-A-Fat is because he's the first one to present. Okay. Well, hopefully he'll. Okay. So yes, welcome. Thank you for coming to the first Shops Colloquium. Hopefully, like Andrew said, it won't be the last. So yeah, real quick, there's going to be 4 presentations, probably all going over time, so we're going to try to get through them quick. We're going to have each one with questions after, so like after each presentation. So don't wait till the very end because topics will be different. So 4 question sections, yes. Okay. And on that, James Fung-A-Fat, if you would come up and get us started.
All right. Show me how to advance slides.
You can clicker or you can push down or right. Up to you.
Down or right? Okay. All right. All righty. So I'm James, and with the electronic shop. And let's see, down or right. There we go. I said electronic shop, but eLab, whatever. And get to kick off, like I said, the first of these. So I'd like to say that early on in JILA's existence, in the early 60s, I think the scientists realized that there's value in having shops, hence instrument shops, and then maybe a little later electronic shops. And so that's sort of where we began. I look back and I think the first hire for electronics was back in '75, and I came on board in the mid '80s and with Terry. So, pardon me? Was there a shop before that? Okay, so see Judah for the ancient shops, right? So here's what the present shop looks like, and Kyle is our present leader, and he is right. Let me see if I have this. So right there, that's Kyle, and he introduced us. And then there's Terry and I, who have been there since, like I said, the mid '80s. And then there's Felix and Yvonne. And just to tell you a little bit about ourselves, just amongst us, there's probably almost 100 years of institutional knowledge. I'm rounding up a little bit, but pretty close. So if there's any questions about, well, not quite ancient, right, Judah? But if there's any questions about at least going back to the late 70s, early 80s, we can probably answer them. We've been around for quite a while. Yvonne, who's down here in the bottom, was just hired on about a year ago, and he did his postdoc at NIST, and then did some work in Europe, and then we hired him, and he's sort of our RF guy at the moment. Felix, the tall guy between Terry and I, did his postdoc here at JILA, and then now he's working with us. He's sort of our digital FPGA guru type. I'll leave Terry here. I'll come back to him in a minute, but I'm sort of a generalist, and you can come in and ask me almost anything, and I'll tell you where to go. All right? So why have electronic shops? We are here to advise postdocs, grad students, and even scientists sometimes on their electronics issues. We're here to train people on how to do things better or do things right. We design, we build. A lot of times, you can't go out and buy the kinds of things that our scientists require to do their experiments. And so we end up designing and building some of these things. Sometimes we go out and we buy things that are out there and designed for one purpose, and we'll repurpose it to work in our labs. We also repair, calibrate. We maintain a loaner set of equipment that you can come and check out and borrow. We used to keep the stockroom up for electronics, but now we have our friendly greeter because, of course, we are quite an intimidating group. And so we got Scott here. So when you come to S275, where we're located, he's our welcoming face, and he keeps up our stockroom. So what do? We herd electrons. We wrangle them into places that maybe they wouldn't want to go, or maybe they don't like to go. And so we have tools. So we can store in places. We can decide where we want them to go. We can decide how fast they get there, or how slow they get there. We can sort them. So if electrons are doing things, and we can characterize them by how fast they are, or how energetic they are, or whatever, we have tools to sort them. We can decide where they go. So sometimes they want to go one place, and we say, no, we don't want you there. We want you over here. And so we have tools to do that. We also think about the fields that these electrons create. So in other words, when electrons are moving around, they create fields around them, kind of like when you move around, there's air going by and stuff. We have to be careful and understand what these fields are doing. And then we get electrons to do work for us, right? Maybe they light the lights, they heat the building, and in our case, they do interesting science for our scientists. Once we are able to herd them and wrangle them into the places where our scientists want them and keep them out of places where they don't want them. Okay, so if you think you have a problem with where electrons are going, invite you to come to S275 and talk to one of the 5 of us. So this is sort of my transition here. I had 2 minutes. I don't know how far. Maybe I went over time. But sometimes us herders or wranglers are around long enough, and we learn enough things, and we experience enough things, and we become a guy like Terry. He's I consider sort of a guru or a legend around here, and a lot of the electronics that we've done in the past, Terry has had his hands on it and his brains on it, and so I'm going to invite him to come up and share with you one or two of sort of the electronics he's done. And there it is.
Thanks, James. So this, I had almost zero time to get ready, so I just pulled up something I've done in the past. And this is a resonant photodetector used in Junyi's stable laser experiment. And it's a cryogenically cooled silicon cavity with super high finesse. I'm not sure if everyone understands what that means, high Q resonator. Part of the issue is you put laser light in it, the power builds up inside and heats up the mirrors, and then the mirrors have thermal noise. And that sets one limit to the stability that they can get with the laser. So the higher the sensitivity of the photodetector we can make, the more they can turn the power down, lower thermal noise, but at the price of lower signal to noise. So the idea is that there's some bottom, and they were kind of looking for the bottom. And a lot of this happened just pre-COVID. And anyways, so the kind of the star of this circuit, well, here's the photodiode that converts photons to electrons. This coil here is hand wound, high Q, low loss, and this dual gate FET is connected like a cascode, which maybe not everyone knows what that means. So these three elements really form the main part of the circuit and allows low noise performance. So the light goes two paths. The DC light goes straight through the inductor into this standard transimpedance amp, which means it just converts the photocurrent into voltage. It also forces this point to be ground, which sets the biasing of this FET. In some ways, electronics can be done with smoke and mirrors and wires. Hopefully not too much smoke, but it does happen, that's for sure. So these are mirrors that actually help bias this transistor. And I have to admit, the circuit is overly complex, and I've simplified it quite a bit on the next version, but I didn't have data for that. So yeah, so that's that part. Let me see. I need to. So this is just power supply filtering. If you have a noisy power quiet circuit, that noise goes through. So filtering power supply becomes pretty important. So this is some raw data from the detector. I mean, some of you understand shot noise. So I shine a flashlight on the photodetector. The fact that electrons are flowing through semiconductor causes shot noise. It's just that the electrons don't come out exactly in order. So the blue line here is the output of the noise at zero light. And then I shine the flashlight on it and I get this green line. And that shows my amplifier's response to the shot noise, which in theory isn't amplitude dependent. At any rate, the ratio of those two kind of give me the idea of where the resonance is at. And the reason why the peak is in the wrong place is that there's some phase shift in the circuit, which would be harder to explain. At any rate, based on those two plots, I can calculate the gain and the noise floor of the amplifier. So in this case, you can see the gain does have this resonance nature, and the noise drops down. So the noise is going down. This is 0.1 picoamps per root hertz. I guess that would take a little while to explain. And this is the bottom, so it's 0.149 picoamps per root hertz. And if I convert that to equivalent optical power, that noise floor is equivalent to 63 nanowatts, which is definitely, well, it's the best one so far, but there's the next version I'm working on. And but the pandemic kind of stopped that at that point. At any rate, the hope for that one is to get below 10. And just, so this is the noise of that DC channel, which sometimes they care about. Wait. I guess it's not exactly changing pages. Okay. Finally, there's the picture of this detector. It's definitely hacked. It would oscillate until I put this copper shield inside. And actually, those screws, if they're not tight, it'll oscillate. It's just unwanted feedback. And the inductor's handmade, and it goes right there. And I just have Okay, how'd I do that with the pointer? That's a good question. Oh, I crashed the whole system. Oh, okay. Oh, that was perfect. So it was perfect timing because I'm done. And I guess if there's questions, we might have a couple minutes for that. I don't know.
Yes. Yeah. Any questions?
Great, thanks. I'm wondering, so when you're designing these circuits, presumably they get logged into some system, but do you upload them to a database that gets used for other institutions, or are they just for local JILA uses?
I think occasionally we build it for other places. Usually not the latest and greatest, and but a lot of that, like in this case, most of the time was paid for by June. So if someone wants one, I'll ask June, and he'll let me know what he would like. But it's certainly a possibility. We made other stuff for other groups.
So I think you alluded to, I think it was 63 nanowatts or 53 nanowatts at 1550, and you said that's the best. And I think in conversations we've had in the past, you've mentioned that sometimes you make things, or the eLab makes things that are better than what you could get commercially. So to what degree does that compare against the best product you could buy?
Yeah, I don't really have anything to compare with, or any resonant detectors that I've seen that have been published. I mean, the key is, like, if I made a DC detector, I can beat that, but we don't want it at DC, so that adds the one of the tricks. But
All right. Well, should we move on? Since we're
yeah,
awesome. Thank you, Terry.
Thank you.
Calvin.
Hey everyone, I'm Calvin, Schwadron. I work in the instrument shop. I've been an instrument maker for a few years now. I started in 2015, and I'll be talking to you a bit about one of the projects we've done in the instrument shop. I don't think we have anywhere near enough time today to talk about all of the rich history and all of the things that the instrument shop has achieved since well before I was born, but we'll just talk about one project, and it kind of ideally will give you an idea of how projects go in the instrument shop. So many of you come into the shop all the time and have something you wanted us to do, or maybe something to fix, and we're working on something, and it's like, what were you working on just now? So that's kind of the aim of this talk. As many of you know, we're the joint institute between NIST and JILA, or CU, and NIST had an instrument shop, and they shut it down years ago. So now we are also the NIST instrument shop. So when things like cesium clocks need to be rebuilt, we're the ones to do it. In this case, we rebuilt the F1 clock, which hadn't been functioning properly, and yeah, we're the ones to take on that job. So how does a job get started? How do we actually, go through the process of, like, beginning a new project all the way to the project running and the experiment taking data, and in this case, setting the time standard for part of, if not the rest of the world. So first off, you start with the idea. In this case, Vladi Gurganov from NIST, who runs the F1 clock currently, had the idea that this isn't functioning right and we need to tear it down, start over, and ideally have something that's much more reliable, because a cesium clock, if nothing else, needs to be reliable. It's not going to be nearly as accurate as a strontium clock or any of the other, super high accuracy clocks that we've also worked on throughout the years in the JILA instrument shop. But instead, it just needs to take time, year-long, and set the length of the second. So he has this idea, came into the instrument shop, talked to, I think initially just spoke with Hans and Adam. They had some back and forths about like, how is this going to be manufacturable? How is this even possible? What's going to be easiest or hardest? Doing that saves a lot of money sometimes. If you come to us and are like, can you make this? And we're like, no, but we can make this instead. That might save you a lot of money instead of coming with a design and it's like, figure out how to do this. So that saved a lot of money, a lot of time. Adam was like, if it's round, why don't you just make it square? Then we can hold it in a vise. Saved me so much time doing that. So good job on that. And then the next step is probably making a CAD model, something like that. In this case, Vladi has pretty substantial SolidWorks skills. So he did the designing. A lot of times the instrument makers in the instrument shop would do the design part, but we did more of the finalizing details and revisions and getting things exactly right, making sure holes line up with each other, making sure we have the right fasteners and are using all the right materials for all of these things. And then we got to actually make the thing. So we don't have necessarily specs and tolerances and all of that to really, go off of a sheet like a machinist might have. The instrument makers kind of have to figure that out. We have to figure out like, what kind of tolerances do we need to make this thing fit right, work right, not, be an interference fit and not go together at all. And since we're making all the parts, we get to make them all fit together. After that, do some testing. Vladi brought some equipment over and set up in the shop and basically was able to like test this cavity, make sure it's working the way he expected. And if it isn't for some reason, then that's where we'll start working on revisions. So the redesign, ideally, most importantly, it's robust. It's got to work. It can't be up for 10 seconds and then down for 6 months. It needs to be running quite often, unlike some of the super experimental clocks around here. We were also in a pretty big hurry to get this done, so we wanted it done fast. And accuracy has an asterisk next to it because, yeah, we want it more accurate than the last clock, the last cesium fountain clock, but not going to be anywhere near as accurate as, like I said, a strontium clock or something like that. So once we get all the details finalized, we'll start the manufacturing process. I ordered some copper blocks, spent a couple $1,000s on copper, and we kind of just got started. There's our CNC machine. These are some of the tool paths on there. There's Adam pretending to use a lathe. Moving on, the whole shop ended up working on this project. So I was working on some of those cavities. Adam was working on some of those mounting parts. On this is James's desk. He's working on some of the end caps for this. All of the parts have to fit together eventually. So we're all taking measurements of each other's parts and verifying that everything is the way that it was in the model that I got, because he changed the model. So now I have to change my model too. Sorry, what's that? I can only imagine. I don't really know how clocks work, but it must be involved somehow. It wouldn't be in this photo otherwise. No, that's James's baby, Margot. Yeah, so I've mentioned microwave cavities. Some of you probably either have no idea what that is or are an expert and are going to be looking at me like I have no idea how they work, which you're right. But I had to make one. There's me pretending to use wire EDM. Yeah, basically the idea is that you've got this cylinder inside of the part. You've got two end caps that go on top and bottom of it. And then inside of that copper piece, you have an empty cavity. And inside of there, you can send in microwaves and they'll resonate. Ideally, you want them to resonate at the frequency of cesium. And you can change that by changing the volume of the cavity. Super basic. Please don't test me on operation of cesium clocks. So I was using this wire EDM. I should go back. This is one of our newer machines, and it is both our most accurate, most precise super capable of certain things, very frustrating to use at times. What it can do really well is it can cut really straight. So inside of this cavity, I wanted the walls to be very straight, very accurate, very round. This is our most precise machine. So I was like, that's how we're gonna go about this. And inside you can see the surface finish that the wire EDM leaves. It's very flat, very smooth, not quite porous, but like matte finish. And so we're like, yeah, that should be fine, because the frequency that we want these microwaves to be at should be about 1 centimeter long. They shouldn't worry at all about surface finish in there. And so the next step is testing. So Vladi brought his equipment over, set it up, started testing it. The cavity is kind of inside of here. And yeah, he's like, okay, the frequency is about what I expected based on how much material we still have to remove, because we're going to have to tune this thing manually by machining out material and then lapping out material, and then the final stages will be temperature to kind of grow or shrink this cavity to get it to just the right frequency. And he's like, okay, it's about where we expected, but we have like nowhere near high enough Q, which is the quality factor, which for those of you who don't know, it's maybe like if you had a tuning fork or something like that, the frequency of that fork would be the frequency. We had that about right, but if you hit it and it only rang for like a moment, that would be like a very low Q. You want it to ring for a long time. And we're like, why is that Q so low? So we took it down to Curtis in the Keck lab, where he's posing in front of his profilometer, and took some measurements of what that EDM surface looks like. And it looks like a forest. It's just this is blown up. So we have about 0.5 millimeter square, and then the z-axis, the height of these spikes, is on a 10 micron scale. So it's super exaggerated, but we've just got like little tiny spikes everywhere because of the way the wire EDM works. It's kind of like, this wire is going along the surface or very close to the surface, and it's charged up, and it sparks and arcs to the material, and that kind of ablates the material, washes it away. And so you take off all the high spots, but you're also, I guess, taking out low spots too. And we're like, well, that wasn't what we were expecting. Possibly this could be affecting the Q. Microwave physicists are shaking their heads right now. So if you looked at a machine surface, like I think this is just a section of that, the end cap, we've got a roughness value, which there's different ways to measure it, but we're going to use the term RA. It's 160 nanometers. This was 800 nanometers, very rough. Lower numbers are less rough. And so we're like, okay, well, we probably need this a lot lower. So we tried hand polishing. But as you can see, this is again blown up z-axis, but the whole diameter of the part. And so we've removed more material from the inside where it got a little bit shinier, and less material from the outside. So it's like, okay, if we have to tune this thing to a couple of microns, like, how are we going to then polish it afterward? We're going to have to remove material to get this thing shiny. So we tried single crystal diamond turning. This is a normal lathe tool, but then it's got this little tiny piece of single crystal diamond, lab grown. So you can get normal diamond tools, which are sintered little chunks of diamond. This is a big solid chunk of diamond on the end. And the advantage is you can get it really almost infinitely sharp on the edge, whereas little chunks would be not nearly as sharp. And this scale's super blown up, but we're getting an RA of 16 nanometers, which is a whole lot better. And I can take super light cuts on the lathe. So I was taking, I think, 5 micron cuts or something like that. And so we can pretty precisely take material out of here. And once we've taken the material out, we have a super high surface finish. So that's kind of like, ideally, done. So more than the hand polishing, we've gotten flatter, we've gotten better surface finish, and now we have a strategy for tuning. These are the same scale on both, but on the left, we've got just a little bit of dish, which is a result of the machine being, I think, 1 micron over about like an inch out of square, which is pretty good for a 1960s lathe. So then we try tuning, and we do the same type of tests. So Vladi would come in and take a measurement in the morning, tell us, okay, we're about this far away. I want you to take this many microns off, which is like barely possible on the 60s hard-inch lathes. And so he'd tell us, I want this much material removed. We'd set it up. It'd take like half a day to get this thing set up perfectly square, touch off, measure it like 5 times, take like 1 cut, or maybe like 3 cuts. And then that's like half a day. And then we'd clean it, assemble it, let it sit overnight, and then he'd come in the next morning and take another measurement. So when you come in and they're like, oh, I want this part to be plus or minus 5 microns, say, it's like, well, this is what we have to do to get 5 microns. It's going to take days and days and days to try and nail something like that down, which is usually not within the scope of what people are asking for. So leave the tolerancing to us. Yeah, and so that was challenging. We got this thing tuned right. Vladi's setting it up right now. So far, so good. This was just one of the challenges of this enormous project. We also have a picture of Hans posing in front of his soldering jig. He's working on the wires here. These coax cables had to be super precise. This was one of the problems that the clock went down in the first place, was because there was some short, I think a faulty wire that wasn't connected right. There were some other problems, but it's like inside of this vacuum that has to be super robust, you can't go in and tweak things, as a lot of you know. So we wanted to nail that all down. He spent a lot of time figuring that out. Getting the protrusion of this pin just right is another factor for tuning. So there's a lot of messing around with that. I'll probably have to rush through this. So there's some parts that Adam made. He made a whole bunch of these lids, had to make this thing for holding the cables in place. There he is posing in front of that machine again. We've got vented screws. So we bought titanium screws, but we couldn't get them vented. So you want the air to be able to come out through the screw, so it doesn't get trapped at the bottom of the hole. He's got tiny little holes drilled in some titanium screws. That wasn't easy. But there it is. That's the whole thing assembled outside a vacuum. I think Vladi's been working on doing the wiring currently, and is going to get it in the vacuum hopefully in the next couple weeks and start baking. But that's how you build an atomic clock. Yeah, any questions? Do I have time for questions, or am I out of time?
We can do 1 or 2, maybe.
Okay.
Quick ones.
And if anyone else has questions, you can always come by the shop, talk to any one of us. We all worked on this project.
So one simple question. Did you work also on the oven that provides the cesium?
I think Hans is currently working on that. It's one of the last things to go into it, but we have basically cesium ampules that'll have to get attached to the outside of the chamber, and then from outside of vacuum, we'll squeeze it and break that ampule. And then I think there's an oven already figured out for that. I haven't actually looked at the oven part, so it must be all dialed in because I had never heard of it.
Okay, thank you.
Yeah. Cool.
Anyone else? All right. Well, thank you, Calvin. Curtis, tell us about what you do down in the Keck lab.
Sounds good. All right, so continuing with the theme that you may not have really noticed, I mean, Terry talked about a job he did for a group here in JILA. Calvin expanded that out to our partners over at NIST, and I'm going to talk about, with my 8 minutes that I have, a job that I and Dave and Mark Carter did for NASA. So specifically, it was for the Europa Clipper mission, which will launch in about 2 years. All right, so just briefly, the Keck lab, what we are, I mean, we're a nanofabrication facility and an optical metrology lab. We can do chip scale and wafer scale fabrication, optical thin film coatings. We have a full metrology suite. So come to us if you have any needs that would be fulfilled by those tools. And primarily, even though I'm not talking about a job done here for JILA, we are here to serve JILA, right? That's our primary purpose, but we're open to campus and the broader community as well. And we're both a user facility, so I can train you how to do all of this stuff on your own. And we're also a job shop, which is clearly what I did for NASA. So, and Dave and Mark. So acknowledgements should go first, especially because I swooped in right at the last minute on this project and got to actually make the final device. but the lion's share of all the legwork was done by Dave Alkenberger and Mark Carter. And then I'm going to briefly talk about a current project that we're doing for NASA as well that Amy Akiri Wong, my colleague, has done a lot of work on. Okay, so LASP is how we get these jobs for NASA, right? That's another CU federal, NASA partnership, very similar to how we're partnered up with NIST. And they've been around a long time. They were founded, in 1948 as the Upper Air Laboratory. And you can tell they've been around a long time because this guy's smoking in the lab while he puts together an instrument in a rocket, which just doesn't sound like a good idea. Maybe they still do this over at LASP, I'm not sure. But so they predate, yeah, great for the optics, that's correct. Like I said, they predate NASA actually, so that's a fun fact. And I believe, Dave, correct me if I'm wrong at the end, but our partnership with them started around 2004 when Dave coated some Mylar sheets with gold that actually ended up on the New Horizons mission. And for those of you that don't remember, that's the one that took those beautiful images of Pluto. So JILA had its hands in that. Okay, so for those of you that know Dave, you won't be surprised. He did a great job. So they came back in 2016 to him to coat another part for another instrument, and this is the one that will go on Europa Clipper. So it's the instrument itself is called the Surface Dust Mass Analyzer, and the part that we coated is the target, which you can see down here. So as dust comes in, it's going to be impacted onto that target and then fragmented into ions, and those are collected on an MCP, and you can get a mass spectrum out of that. So the Europa Clipper, it's one of NASA's flagship missions, so it's really exciting that JILA got to work on it. And this instrument itself is going to be looking at the mass spectra of dust particles that are in the upper atmosphere of Europa. And the idea is to look for signatures of life. So if there's life in the oceans beneath the ice on Europa, and an asteroid comes in and smacks into that ice, hopefully some of these chemical signatures of life will be launched up into the upper atmosphere in the right place where this instrument will come and fly through and detect it. Okay, so LASP figured out they have this dust accelerator. That's one of their claims to fame. And they figured out that they need an iridium coating that's at least 250 nanometers thick in order for this thing to work. So these dust particles are going to be going very fast relative to this instrument. You don't want them just punching straight through your coating and not being detected. So iridium is extremely hard metal, one of the hardest, and it's also one of the least reactive, if not the least reactive. The only thing it will react with are molten salts. So you can't take an acid and get rid of iridium. It's not going to work. That's actually how it was discovered. It was the sludge at the bottom of the beaker when they dissolved platinum with aqua regia. So all these facts about iridium also make it very difficult to coat onto a substrate. It doesn't want to play nice with any other material. So Dave and Mark built a custom chamber addition to one of our chambers that's in the clean room. And basically, here's that target that LASP had made and polished and then delivered to us. And it gets mounted in the chamber right here, and we have some heaters to heat the thing up. And then this all gets mounted onto the chamber right here. This funny shape that you see, that's Mark Carter's design. He did the math to figure out, okay, if this target is rotating in the chamber, and we have a magnetron kind of down here at the bottom, how are we going to make sure we have the same thickness on the inside radius as well as the outside radius if they're moving at different speeds? So he came up with this design, this cutout mask, and it worked great. But we had some problems, and this is right when I started. These quartz heaters that LASP provided for us, they kept failing, and that's because we have to heat this thing up beyond 400 degrees Celsius in order to get the iridium to stick. And these quartz heaters, they just were blowing out, usually before we could even start coating iridium. So then, the thing was hot, but we'd have to just coat iridium as it just coasted back down to room temperature. And that caused just this terrible surface finish because we had bad adhesion. And you can actually see some of the iridium peeling off of one of these witnesses right here. So we thought back to, I think it was my instrumental analysis class, and in order to get tungsten to not evaporate from a bulb, you just use a tungsten halogen bulb, right? So the halogens and the oxygen inside the bulb are going to react with that tungsten that's evaporating off the filament and then redeposit it back onto the filament, so it's going to last longer. And that solved the problems. We were able to just get all of these done literally in the nick of time once we once we did that switch. And forgive me, I'm highlighting one problem that we had with this. This was not the only problem. Dave and Mark solved tons of problems, but I don't want to keep you here till 5 p.m. So this is the one I'm going to do. All right, but we were able to finish it up. And you can see here, if you can read that, on NASA's main page on the Europa Clipper, they have this readiness level, and hardware delivered is under SUDA. So we've done it. These are pictures from LASP as they were actually assembling that mass spectrometer. That's the disk that we actually coated with iridium. It's being put at the bottom of the instrument. And then here it is, completely assembled, has this door to protect the instrument when it's not in use. And you can kind of see the iridium plated disk there at the back when the door's open. And then this thing has actually been delivered to JPL at this point, and they're actually strapping it onto the main spacecraft as well. And it has a nice little CU symbol on it. They didn't put JILA. I'm a little offended by that, but Okay, so real quick, we did that one dust detector for LASP, and so they came back. They said, "Can you do another one for us to go on the IMAP mission?" An instrument called IDEX, the Interstellar Dust Experiment, and it's the same type of instrument. This time they needed 5 microns of gold, and the disk is 16.5 inches in diameter. So at first we were like, well, we're not set up to do thick coatings like that, and we don't have a chamber big enough to do it. But the vendors that they went to couldn't deliver on surface roughness. So we delivered for SUDA a surface quality that was so good that the engineers at LASP told us that it will be 3 orders of magnitude more sensitive than any other dust mass spectrometer that's flown in space before, which is really cool. So they, we spoiled them. And when the vendors couldn't provide that same quality, they came back to us and said, we really need you guys to do it. So Dave came out of retirement to design this chamber, and we've built it. As you can see, there's a photo of it. And it's large enough to hold this very large disk. And it's very simple on the inside. It has 2 magnetrons that point up, one for coating an adhesion layer of titanium and another for the gold. And you can see we used Mark's design again on this mask to get an even thickness across this even larger disk. And this is the work that Amy has done. So she's coated these 2 already. This was just an original, like, can we actually do it? And it worked. This is the engineering model. So this is that one that LASP is actually going to use to test the instrument in their dust accelerator. So you can see here some pictures of LASP putting together that instrument. Just really pretty pictures, right? And that's about it. So any questions?
Anyone?
That yellow color. That's the color of iridium.
For this?
Yeah.
Okay, no, I probably breezed through this too quickly. This is the IDEX one, the second one that we've been doing.
Oh, okay.
And it's gold. So iridium is like it's a silvery metal. It's hard to tell in this picture, but it's actually a lot more white than like silver. It's a very, but you can't really tell from the photo. Yeah.
Hi. I think you were saying you have to heat up something, but was it the target,
Yes.
the plate? Why do you have to heat up that?
Right. So in order to get the iridium to stick on the target, we had to get it really hot so that it basically is kind of annealing as that material is coming down, and you're not getting stresses building up on that material. That as soon as you're done, those just kind of pop up and the whole thing peels off like a sticker.
Did you have to cool it down carefully afterwards? Or?
We just carefully, but yes, we would let it sit in the chamber for about a day. That was our careful procedure. Yeah.
Thanks.
What's the flatness of the 5 micron coating across the entire wafer?
That's a good question. So thankfully they didn't have tight tolerances there. It's like 10 or 20 microns. But the surface roughness, so flatness being like, is it just, could you put a ruler on it and it's touching the whole thing, right? No. but the surface roughness is the kind of microscopic scale, and that's about a 2 nanometer RMS. So,
Thanks.
yep.
All right. Thank you, Curtis. Get back. So last but not least, Felix is going to tell us about future of shops. So the shops are ever changing, and this is a collaboration that electronics is doing with computing. So
Yes, yeah. Thanks, Kyle, for the introduction. As you may remember from James's introduction early on, I'm actually part of the electronics shop. But I'm sorry, I should get to the title slide too. But this is actually something that I'm doing together with Corey, who's over in computing, and also right here. And instead of just focusing on the performance, one of the problems that we want to address with this is basically the question of how do you get the performance that you want, but you also build in enough flexibility to your systems so that the process of prototyping and getting things off the ground isn't long for weeks and months, but we're trying to be ready faster, be able to do more projects for cheaper, but still keeping the performance that an FPGA can give you. So FPGAs, as some of you may know, have very high performance. They hold timing very well, and they can do a lot of things in parallel. Which is why we use them over the years to do a lot of waveform synthesizers and controlling things that are very sensitive to the exact timing. Some of the examples are on here, and the general theme to this point has been the signal generation. And over the years, we've done more and more projects, and unfortunately, if you add enough features to what started out as a very simple design, that's usually what it ends up looking like, and these things just become very hard to work on and very hard to maintain. And the process of keeping all of these little wires on the FPGA not tangled up is very time consuming. So what we're trying to do here is to reduce the complexity that is in the wiring itself, and instead of sacrificing the performance where it's necessary, we're just trying to untangle the wires that are sort of in the user-facing, user interaction, and because that's actually not nearly as sensitive for the performance as the critical part that's on the FPGA. So what we're trying to do now is get away from these entangled circuits and replace the flexible part. Let me see, this one? The flexible part with the CPU, just like your desktop computer, where you can do accounting on it, you can design cesium clocks, you can do Terry circuits. It's really flexible, but you just don't know exactly when things happen. So all the sensitive and critical things are going to be down on this FPGA end, and we're working on the infrastructure to basically allow us to do the quick prototyping and changing, tweaking different setups and boxes, configurations for different labs, while keeping the performance of the FPGA. What I found, looking for the best solution was to actually not have us do it and develop it from scratch, but to run with something that's actually supported by the FPGA vendor, Xilinx in this case, that we're going with. I have adapted this and been playing with it. I think it's about ready at this point to actually, incorporate it into a real project. And the idea is that we would do these upper 2 layers, or we would do these down 2 layers where all the critical part is down here, FPGA, that's all the timing related stuff. Then there's a software layer, and we're basically going to cut it here and expose this to students and postdocs and basically provide them with, it's a Jupyter Notebook interface that you can open up in a browser and you can program and, call different functions and make, basically pass it through the stack and then get the FPGA to do the things that you need done. There's some challenges in, how exactly do you have these non-critical parts with, interact with the critical parts. And that's actually sort of the biggest challenge that I'm still facing, so that the non-critical things don't basically slow out the critical pieces. but the immediate goal at this point is to adapt that framework and port a laser servo, or just a general servo design that has come out of NIST about 10 years ago, I think. I should probably know the exact year, but it's been, a fairly long time. And while that design has found a lot of use over at NIST as well as inside JILA, unfortunately, the chips are sort of going out of fashion, and the circuit itself is just not as flexible and user-friendly as they would like it. So we took this on as our first project to basically use this to demonstrate, the capabilities that we can get through the new user interfaces. And I've been trying to get this ready for this presentation, but have not managed to get there quite yet. So stay tuned, but that should basically become available over the next couple of months. And once I have it, I hope I can show it off to people. Or if you have interest in being like a beta tester, please come by, let me know. And I'll be happy to give you an early unit for testing and evaluation. With that, I would like to mention that there's other technologies that we would like to, or that we're currently working on adapting. So we're trying to get one of these RF socks right here. Without going too much over time, they have these very fast data converters, so they can sample at 5 gigasamples, and they can output waveforms at about 10 gigasamples per second. So these are great for direct RF and microwave synthesis. Kyle, our leader, has been in touch with all the people doing the paperwork, but we are hoping to actually get one of these units that we can use to actually do a servo and a demonstration unit with towards the end of the year, hopefully maybe early next year. And if you have any interest in this direct microwave synthesis, for instance, also please, shoot me an email or come by. I'll be happy to kind of use you as a beta user. And then last but not least, despite the shortage of FPGAs that people might be aware of, there's actually a few modules that one can get that are not nearly as expensive, but also not nearly as powerful as these. And one of the things I would like to do is just design basically a carrier board that these little modules can go on, because what you typically get is communications or hardware acceleration for computing oriented, or maybe vision like camera stuff. But there isn't really any platform that has, ADCs and DACs or lab interfaces basically available right out of the box. So I'm looking at efficient ways to make that basically available for everybody in JILA. And with that, I would just like to thank you for your attention and see if there's any questions. Yeah, if I got it. I thought I had 8.
Yeah, I was actually going to say we're doing well on time, so I'd at the end of this we can open it up to just more questions
So
if anyone thought of
minutes.
something
Yeah,
else.
I thought it's 5 minutes for questions. But yeah, if we can cut into that a little bit. So I think the interesting part here is actually the comparison between this board here, which not this exact one. The ones you can buy from Xilinx go for like 11 or 12,000 bucks. They are definitely not cheap at all. But in the commercial ones, you get 8 channels each. So if you have a larger setup, these may actually be not horribly inefficient as far as cost to channel or cost to cost per application goes. But as you can see down here, the cheap modules don't come with these data converters. So for lab use, they are essentially useless. And the best alternative that we have found to give you basically, a low-cost module that has an FPGA with the CPU framework and everything sort of combined on the same chip, but also the data converters to get signals in and out, are these red Pitaya boards. And luckily, Ivan, before coming here, has had a little bit of time and some projects to actually work with these, which is why we ultimately decided to use these as sort of the low-cost platform where the frequencies of signals involved aren't very, very high, so in the megahertz range or so. but where the application is a little bit more cost sensitive. And we would just, kind of stamp out multiple of these and give them to people. I guess what about the architecture would be interesting. Oh yeah, the difference about. Yes. Well, it's adding new capabilities in terms of the flexibility and the user interface is concerned. So, for instance, things that like we oftentimes get in as requests is to basically have like a hold function where you can get your servo locked and then you can just sort of freeze it, hold it, do your experiment, relock it, freeze it again. These red batallas with the web interface would actually provide the students or the postdocs who actually need to run these experiments with a very efficient way to interactively use the unit and sort of tweak things up, see what's happening, adjust things as necessary, and then when you're done, you can basically save your profile and then just kind of keep reusing it until you need to tune things the next time around. That is some of the functionality that's not as user-friendly on the old version of the servos. So, that's a big part of what we're adding. As far as the performance is concerned, it would actually be very comparable because, for these units, they are typically used for like AO intensity servos that don't need, huge bandwidth. So it's a few hundred kilohertz is typically what people are looking for. And for those cases, these would also be the most economical choice because you can get the board for like $800. Hopefully students can sort of box them up so that it's not a lot of extra, assembly work and for the shop to put things together and get them ready to go. So hopefully we can make this a more user-friendly, but also, a cheaper unit for people to one day just come by and just, pick up one or two of these whenever they need one. Yes. Yeah, I hope, yeah. So the roadmap or the idea is to have this pink framework and actually adapt it for all of the FPGA boards that we're currently using. So there's a few of these Zinc UltraScale boards that we currently have. And then we have these fancy boards right here and these modules down here. And what I'm currently working on regarding this pink framework here is to actually make this, the same stack shown right here, available on all of these different boards so that the differences in FPGA boards used are sort of abstracted away and people can basically home in and just, use the same user interface regardless of what specific device they're actually controlling with it. So it's also tying all of these different user interfaces together into like one standard, well-defined interface, hopefully, that will also make it easier to take a design from one group and then, implant it over to another experiment in a different group that may be using, different standards and have different preferences for the interfacing. So is that one question I can still take? I'm just like nervously looking at the clock, but.
I think we're doing well.
Yeah, we got 2 more minutes. Yes.
So with the RF system on a chip, the clock speed, well, I guess I'm thinking if you want to make use of like the ADC and DAC and like do real-time processing of microwave signals, don't you need a clock speed that's like many times this 5 gigahertz or 10 gigahertz? Like what is the clock speed? Like, is there a limit on the clock speed?
Yeah, on FPGAs, there is much harder limits than what you get on ASICs because everything, is flexible and reprogrammable. In an ASIC, it's just sort of like hard burned into silicon. So, those things can go quite a bit faster. In these cases, the clock frequencies you can have on the FPGA itself are typically a few hundred megahertz max, 2, 3, maybe 400 megahertz. And what you do instead of trying to basically deal with, these signals every, 200 picoseconds, per data point or so, you just have a whole number of them and you acquire, say, 500 at a time. and then you process all 500 of those in parallel on the FPGA at a much lower clock rate. So you're right in a sense that you can't have a signal coming in at 5 gigasample per second and then expect it to be processed with this 200 picosecond granularity, which is ultimately what would limit us, for a servo, for instance, as far as its bandwidth would be concerned. But the fact that FPGAs allow you to put as many channels in parallel, right, to do processing at much lower rates, makes them so great for these systems that have like a high channel count, for instance, or also just like video image processing, where you have, say 1 million pixels, and you can sort of do the same operation on all 1 million pixels. So instead of having to do this, at gigahertz rates, you just do it once every 10 nanoseconds or so.
All right. Well, thank you guys for your attention. It's I hope we get to do this again, and thank you obviously to all the shop staff here for taking time to put this together for us. So, yeah, that's it.
Because I was like, blah, 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 blah.
Well done, guys. I knew it was YouTube. No, that was great.
Yeah.